Hi everyone, I'm Suzette. I'm a Benzing postdoctoral fellow at the University of Alberta, and together I work with Graham and several other people in our group, also a project related to the Metal Earth project. So today I will be talking about a new discovery of diamonds in a detrital gold deposit from the Slave Craton. And we're going to use these Mesoarchean diamonds to actually look at what was happening early on in the Craton root formation. So we're looking at Slave Craton, which is placed in Canada, as you can see on the map on the left. And particularly within the Slave Craton, we're looking at that very northern part, which we call the Three River area. So if you look in diagram C over here, the Three River area is highlighted with where we found the diamonds and the gold in a conglomerate. So we show an example of the conglomerate over here, and this conglomerate is part of the basal conglomerate section. That's part of the central slave cover group, in which we found detrital gold, zircons, as well as diamonds. So this Canadian diamond gold deposit that was discovered consists of quartz pebble conglomerates. Carbonaceous material was present. It's over 2.85 billion years old, in which I will go into a detail in a moment, and it contained diamond and gold. And this is actually very, very similar to the Witwatersrand basin in South Africa, which contains one of the largest mined gold globally. So about 40% of the mined gold every year is coming from this basin. And again, this deposit contains a quartz pebble conglomerate, contains carbon, has about the same age, and they've also recovered diamonds from this deposit. So today we'll be looking first at the zircons and how these detrital zircons can actually supply us with the maximum deposit age and thus minimum age for the diamonds. We'll also look at some Sumerian neodymium isotopic compositions from the whole rock from this conglomerate, as well as the recovered diamonds and how we can use these to actually determine a geoferm for the Mesoarchean. So on the right over here, you can see an example of the 3 diamonds that were recovered. They have cubic to octahedral morphologies, and on the left, you see an example of some of the zircons that we analyzed. So a batch of 233 zircons were analyzed for uranium leads by laser ablation ICP-MS. And of these 233 zircons, the near concordant and concordant analysis are plotted on these graphs over here. They fall within the 95 to 105% bracket of the Concordia line. And as you can see, the youngest age is 2,848 million years, but we have a main peak at about 2.94 billion years. So in the graph on the right, you can also see that we actually have a very restricted age range from the zircons that are centered around 2.94 billion years old, and that the maximum deposit age is 2.84. The whole rocks, part of the conglomerate was crushed, and very small fractions of about 0.1 gram were actually analyzed for samarium neodymium. And as you can see, the teacher model ages and the depleted mental model ages again have an age range of about 2.82 to about 3.5, again confirming the age range that we also got from the zircons. Because the zircons have quite a limited age range, we have quite a tight histogram, and this actually points to a relatively small catchment area. So likely these zircons came from a relatively small hinterland where the variety of sources was more limited compared to if you, for example, had a larger catchment, which would result in a much broader histogram for the age range of the zircons. So now we will look at the diamonds. So one of the main traces that we can find in diamonds is nitrogen. So even though it's almost built up of 100% carbon, we do get a minor ppm level of nitrogen in diamonds. So initially, nitrogen is present as a single atom. And then with time, the nitrogen aggregates and it becomes two pairs of nitrogen in the lattice structure. And finally, once it's fully aggregated, we get 4 nitrogen around the vacancy. And this nitrogen aggregation is dependent on the nitrogen concentration, the time, and the temperature. So the higher the concentration, or the longer the time, or the higher the temperature, the faster the aggregation will go. So from the 2.85 billion years old that we got from the zircon age, we can then estimate how old these diamonds are. So the oldest diamonds on Earth so far that have been dated are around 3.5 billion years old. So this difference between 2.85 and 3 billion years would give us a maximum mental residence time of 0.65 billion years. Here we have assumed a very conservative time span, anywhere between 10 million years and 1 billion years. Now, when we use these residence times, we can actually calculate the temperature based on the nitrogen concentration that we measured and the aggregation state. So one of the diamonds are at 311 atomic ppm nitrogen, at 4% of the nitrogen in B centers, which means it was fully aggregated for 4%. With a residence time of 10 million years, that would then result in a temperature in the mantle of 1170 degrees Celsius. If we used the longest mantle residence time of 1 billion years, that would then result in a mantle residence temperature of 1060 degrees Celsius. Now we can combine this mantle residence temperature to a pressure to get the geoferm. So this nitrogen-bearing diamond actually contains an olivine inclusion, as you can see on the lower diagram on the left. With single crystal X or D, we could measure the volume of this olivine inclusion in the diamond. And when we have the measured volume of this olivine inclusion, we can use the equation of state and the temperature estimate that we got from the nitrogen to calculate the original pressure at which this inclusion formed. So on the right diagram over here, you can actually see the mantle compositions for olivines. So we've got lertzolytic olivines on the top. These are all inclusions in diamonds. So the lertzolytic olivine inclusions in diamonds typically have a magnesium number of about 92, whereas Harzbergitic olivine inclusions in diamonds typically have a magnesium number of about 93, just over. So what we then do, because the volume of this olivine inclusion is actually dependent on the composition of the olivine inclusion, we can then estimate what the most likely pressure was. So based on the literature data, the olivine inclusion would have been between 90 and sort of 95 magnesium number, but the most likely composition would have been 92 to 93 based on the frequency distribution. So this then results in a pressure of 5.5 to 5.9 GPa. So when we plot this temperature and pressure constraint, we can actually constrain the geoferm. So in the green square over here, you can see our PT estimate from the diamonds, and that results in a geoferm of about 36 to 38 milliwatt per square meters. And this is actually very similar to the xenoliths geoferm from the slave Craton. However, these xenoliths, they re-equilibrated at the time of kimberlite eruption about 55 million years ago. So what we actually see is that the geoferm at least 2.85 billion years ago in the Mesoarchean is as cold as some of the coldest geoferms that we actually see today underneath Cratons. And because we had relatively little time to form this Protonic root with this really cold geoferm, that actually constrains that we must have had quite a quick and rapid formation of the Protonic root. And this has implications for how this Protonic root was formed. So on the diagram on the right over here, we have plotted various models from previous literature studies. And as you can see in the orange over here, these are all geoferms from hot initial state models. So either via plume secretion or from the a large melting event underneath rift settings. And because it was very hot in the beginning, it actually takes a long time to cool enough to get a very cold geoferm in a thick cratonic root. So as you can see over here, from the right to the left, following these arrows, after 20 million years, then after 200 million years, and then the two thicker orange regions are actually after 1 billion years. So in order to get a geoferm cold enough from a hot initial state model, it would have taken at least 1 billion years to sort of get the geoferm that we see in the Mesoarchean. Now, this is quite unlikely to have formed that in that time period. We probably need something that was much faster than that. So then we also looked at cold initial state models like stacking or subduction. So those are highlighted in blue over here. And as you can see, especially in the beginning, we do actually get these cold geoferms that are very similar to the geoferm that we get from our diamonds. So that implicates that we likely had some forms of stacking or mobile lid tectonics, or some form of subduction in the Mesoarchean to form a thick cratonic root very quickly and rapidly. Now, this is supported by the carbon isotopes that we measured in the diamonds. So we've plotted the carbon isotope composition on the x-axis, and then we've got the histogram frequency on the left. So as you can see in the histogram, you can see our free samples, and they plot at quite heavy carbon isotope values. So the mental plots around -5, whereas carbonates plot at heavier values closer towards 0 or even to +3. So our samples have an indication that some form of crustal carbonate was involved in the source of the fluids that formed these diamonds. And our diamonds actually show that they were relatively heavier compared to the slave macro diamonds and the slave micro diamond population that's plotted as a kernel density estimation. As well, our samples are plots on the heavier half or the heavier end of some of the diamonds in the literature that have been dated that were of similar age. For example, the 2.7 billion years old diamonds from the Wawa deposits, around the 2.9 from the Witwatersrand deposits, and some of the slave diamonds. So the carbon isotope supports an initial cold state model where we had some form of imbrication or subduction locally. However, when we look at the southern part of the slave craton, there have actually been detrital chromites discovered that indicates there was a chromatite magma solidified in the southern part of the slave craton. Now, chromatites are very ultramafic, very hot magmas, which indicate there must have been a relatively thin lithosphere presence. So a recent study from Haugaard et al. That discovered these detrital chromites in the same section in the central slave cover group. They were recovered from the faxitic quartzites that's part of the same sequence as the basal conglomerates that we see. These chromites were measured by rhenium osmium to determine an age, which resulted in an age of 3.2 billion years. So this shows that at 3.2 billion years, we had a very hot, thin lithosphere present in the southern part of the slave craton, but at around 2.9, 2.85 billion years ago, we already had a very thick cratonic lithospheric roots in the northern part of the slave craton. So this results in the following model that we then developed. So around 3.2 to 3.5 billion years ago, we would have had plume or perhaps rifting that would have resulted in the thin hot lithospheric mantle that resulted in the chromatites and potentially also the golds. And then shortly after, via imbrication or some form of local subduction, we would have formed these diamonds in a cold initial state. It doesn't necessarily have to have been firmly equilibrated at that point, but at least we must have had a cold initial geoferm to form these diamonds. And then subsequently, these diamonds were brought to the Earth's surface by a type of kimberlite-like eruption. Then, via lateral accretion and early Protonic basin formation at 2.85 billion years ago, these diamonds would have been eroded from the initial original deposits, as well as through the erosion of the gold deposits and the chromite from the komatiite. And this would have resulted in the basal conglomerates and subsequent sandstone sections, where we see the deposit that we got today. And finally, through building of smaller blocks, we would have formed a larger stable craton after 2.7 billion years ago. And eventually, with additional events later on, for example, through the Mesoarchean coming in from the west at about 1.9 billion years ago, we would have formed the slave craton that we see today. So just to summarize, we found a new diamonds and gold deposits in the form of a quartz pebble conglomerate in the northern part of the slave craton. And these diamonds actually show again that they're very similar. This deposit is very similar to the Wits gold deposit, so it has a lot of potential, possibly for the golds. And the zircon ages and the diamond's pressure temperature estimates imply that we must have had quite a small catchment and source area and a very cold Mesoarchean mantle roots, and that we had a very small Protonic nuclei with very deep roots, and that these were as cool as some of the coldest mantle roots today. And there's still work ongoing to find more diamonds. So I just want to thank everyone who's involved in this project, as well as the funding that we got from the Canada Excellence Research Chair, Metal Earth, the NSF, and the Saskatchewan Research Council. Thank you.
Great, thank you very much, Suzette. We have time for 1 or 2 questions. Was there any other trace out, any uranium in those conglomerates or anything else?
Not that I'm aware of, but I haven't looked for that. I would have to talk to my other co-authors if they've looked at the uranium. I'm not sure.
We haven't, Suzette, but that's a good point, Ross. I mean, maybe we should do some more whole rock geochemistry, because with there is that enriched carboniferous layer. Well, it's not a layer, but there's certainly enrichment of organics which can tend to drive up the uranium content, can't it? So it would be prudent to look at that.
Yeah, well, just as a comparison to the bits, which has, you know, significant detrital. Yeah. Yeah,
and actually so the Wits diamonds are interesting because they show clear evidence of radiation damage from a high uranium environment. The 3 diamonds we've recovered from this so far don't as yet, but that's not to say that, I mean, it's only 3 diamonds. A lot more diamonds have been looked at from the Wits.
Just that with looking at the Wits, I think one really needs to distinguish between the more proximal areas with the lower uranium content and the more carbonaceous areas, which would have the higher uranium content. And you might well have a more proximal equivalent with what you're looking at of the Wits stuff. Thanks.
Thank you, Chris.